Alright, let's get into it. Number 8. The Methuselah Star. In 2000, astronomers turned the Hubble Space Telescope toward an unremarkable-looking star in the constellation Libra and measured something that briefly stopped astrophysics in its tracks. The star, catalogued as HD 140283 and nicknamed the Methuselah Star, appeared to be older than the universe itself. That wasn't a rounding error. That was a crisis. HD 140283 sits approximately 190 light-years from Earth, practically next door in cosmic terms, which is precisely what made it so easy to study and so impossible to dismiss. It belongs to a classification called Population II stars, among the oldest stellar types known, formed from nearly pure hydrogen and helium in the universe's earliest moments. When astronomers first calculated its age, they arrived at a figure of approximately 16 billion years. The universe, by the most precise measurements available, is 13.8 billion years old. Something was wrong. In 2013, Howard Bond of the Space Telescope Science Institute led a refined analysis using improved parallax measurements, bringing the estimate down to 14.46 billion years, with an uncertainty of plus or minus 800 million years. That margin just barely allows the star to exist within the universe's timeline. Just barely. The Methuselah Star also moves at roughly 800,000 miles per hour relative to our Sun, a high-velocity wanderer passing through our galactic neighborhood like something ancient and restless. Its near-zero metallic composition confirms it formed when the cosmos was chemically almost empty, in the universe's first gasp of stellar creation. Scientists continue refining the measurements because the alternative is deeply uncomfortable. If our calculations are correct, the Methuselah Star was burning before time as we understand it began. And if our calculations are wrong, we have to ask which measurement we trust less, the star's age or the universe's. Number 7. The ancient quasars. In June 2011, a team led by Daniel Mortlock of Imperial College London published a paper in the journal Nature announcing the discovery of a quasar so distant that its light had been traveling toward us for 12.9 billion years. That alone would be extraordinary. What made it devastating to conventional physics was what powered it. A quasar is essentially a galaxy in its violent infancy, its core blazing with the energy released, as matter falls into a supermassive black hole. The quasar Mortlock's team identified, designated ULES J1120 Plazor 641, had a redshift of Z equals 7.085, placing it at a point in time when the universe was only 770 million years old. Standard cosmological models accept that. What they cannot accept is the mass of the black hole at its center. That black hole weighed in at approximately 2 billion times the mass of our Sun. 2 billion solar masses, assembled in less than 770 million years from a universe that began with nothing but hydrogen and helium and heat. Under standard models of black hole formation, through stellar collapse and gradual accretion of surrounding material, achieving that mass in that time frame is essentially impossible. The math simply does not work. Then, in 2021, it got worse. A team analyzing data from the Magellan-Baade telescope announced quasar J0313 1806, hosting a black hole of 1.6 billion solar masses at just 670 million years after the Big Bang. Each new discovery pushes the problem earlier and makes the standard formation model harder to defend. Theorists have proposed exotic solutions, including something called direct collapse black holes, seeds that bypass the slow accretion process entirely. None have been confirmed. These black holes grew to monstrous size in a universe that shouldn't have given them the time, and every year we look deeper into the early cosmos, we find more of them waiting. Number 6. The cold spot. In 2004, scientists analyzing data from NASA's WMAP satellite, the Wilkinson Microwave Anisotropy Probe, found something embedded in the oldest light in the observable universe that the standard model of cosmology had no framework to explain. In the direction of the constellation Eridanus, pressed into the cosmic microwave background radiation like a bruise on the face of creation, was a region of space roughly 1.8 billion light-years across that was measurably, inexplicably cold. The cosmic microwave background is the afterglow of the Big Bang itself. Light emitted approximately 380,000 years after creation that has been traveling ever since. It is the oldest thing we can observe. Its temperature fluctuations are extraordinarily subtle, tiny variations that seeded the large-scale structure of the entire universe. Those fluctuations follow a very specific statistical pattern predicted by our best cosmological models. The cold spot violates that pattern in a way that is difficult to overstate. The region runs approximately 70 microkelvins colder than its surroundings. That may sound trivial, but in the context of CMB temperature variations, it is a screaming anomaly. ESA's Planck satellite confirmed it in 2015 with the most precise full-sky CMB measurement ever made. The cold spot was real, persistent, and unexplained. In the same year, a team at the University of Hawaii, led by Istvan Chaput, identified a supervoid in the same direction, a region of space containing far fewer galaxies than expected. A supervoid would cool CMB light passing through it. Problem solved, it seemed. Except the supervoid accounts for perhaps 1/3 of the temperature drop. The rest remains completely unexplained. Several physicists, publishing in peer-reviewed journals, have proposed the cold spot is the scar left by a collision between our universe and a neighboring one, an impact that occurred before our cosmos was even a second old. If that is what it is, the question isn't just what hit us. The question is what was already out there to do the hitting. Number 5. The Great Cosmic Web. When astronomers began systematically mapping the large-scale structure of the universe in the 1980s, they expected to find galaxies distributed more or less randomly through space, scattered by the chaos of the Big Bang. What they found instead was a web, an immense, intricate network of filaments and walls and voids assembled across hundreds of millions of light years, structured with a precision that the universe, according to our models, should not have had the time to achieve. The cosmological principle, the foundational assumption underlying all of modern cosmology, states that on the largest scales, the universe should look roughly the same in all directions and at all locations. Structure should exist, but only up to a point. That point, derived from simulations and theory, sits at approximately 1.2 billion light-years. Beyond that scale, the universe should be smooth and featureless. In 2003, the Sloan Great Wall was identified at 1.37 billion light-years. That was already uncomfortable. Then, in 2013, Istvan Horvath and colleagues published an analysis of gamma-ray burst distributions, suggesting a candidate structure they called the Hercules Corona Borealis Great Wall, potentially spanning somewhere in the region of 10 billion light-years. That is nearly 1/10 of the observable universe. If confirmed, it would be approximately 8 times larger than any structure that should theoretically exist. The cosmological principle, the bedrock of our understanding of cosmic structure, would need fundamental revision. What makes this particularly unsettling is that cosmic filaments are not random. They trace the imprint of quantum fluctuations from the universe's first fraction of a second. Density variations so small they existed at scales smaller than an atom, stretched by cosmic expansion into the architecture of everything. The web was written into space before the first stars ignited. Something encoded the blueprint of the entire cosmic structure in the first instant of creation, and we are still learning the language it was written in. Number 4. The Echo of Creation. On March 17, 2014, a team of astronomers at the BICEP 2 telescope at the South Pole, led by John Kovach of Harvard University, called a press conference that the scientific world had been waiting decades for. They announced the detection of a specific swirling pattern in the cosmic microwave background, a signal called B-mode polarization, which theory predicted would be left behind by gravitational waves from the first 10 to the power of negative 32 seconds of the Big Bang. They believed they had captured the literal fingerprint of the moment of creation. Inflation theory proposes that in an unimaginably brief window after the Big Bang, the universe expanded from quantum scales to macroscopic ones at a rate that defies intuition, and that this expansion should have generated gravitational waves powerful enough to leave a permanent imprint on the oldest light in the cosmos. Detecting that imprint would have been the greatest observational achievement in the history of cosmology, direct physical evidence from a moment before anything recognizable as physics existed. By September 2014, the announcement had unraveled. A joint analysis between the BICEP-2 team and ESA's Planck satellite revealed that the signal was consistent with a far more mundane source: polarized dust within our own Milky Way, contaminating the data. The detection was not confirmed. BICEP and its successor instruments have continued operating, setting increasingly precise upper limits, with the most recent BICEP Tau Keck results from 2021 placing the tensor-to-scalar ratio at less than 0.036. The signal, if it exists, is hiding just below what we can currently measure. This is what makes the situation genuinely eerie. The mathematics of inflationary theory strongly suggests the signal should be there. The echo of creation should be audible. We have simply not yet built instruments sensitive enough to hear it above the noise of our own galaxy. Somewhere in the ancient light above us, the scream of the universe's first moment may still be reverberating, and we are standing just outside the room, straining to listen. Number 3. The rings before the beginning. In 2010, Sir Roger Penrose of the University of Oxford and Vahe Gurzadyan of the Yerevan Physics Institute published an analysis of WMAP cosmic microwave background data that made a claim so audacious it rewrote the terms of the conversation about what existed before our universe. Embedded in the oldest observable light in existence, they said they had found concentric rings of anomalously low temperature variation. Those rings, according to Penrose, were not artifacts of our universe. They were echoes from the one before it. Penrose had spent years developing a theory he called conformal cyclic cosmology, or CCC. The theory proposes that our Big Bang was not the beginning of everything, but the beginning of one aeon in an endless cycle. Each aeon begins with a Big Bang and ends in a cold, empty, expanding state in which only massless particles remain. At that point, time itself loses meaning. The geometry of that dying universe becomes mathematically equivalent to the geometry of a new Big Bang, and the cycle begins again. The previous aeon's supermassive black holes, evaporating over timescales of 10 to the power of 100 years, would release their final energy as Hawking radiation, and the imprint of that radiation would survive the transition, pressed into the CMB of the next universe as faint concentric rings. The rings Penrose and Gurzadyan identified in WMAP data appeared at multiple locations across the sky. Subsequent analysis using data from ESA's Planck satellite identified further candidate ring systems. Independent researchers challenged the statistical significance of the findings, arguing the patterns were consistent with noise in standard cosmological models. Penrose's team published detailed rebuttals, and the debate has not been resolved. In 2020, Penrose was awarded the Nobel Prize in Physics, not for CCC, but for his foundational work on black holes. What the rings represent, if real, is something that should not be possible to possess. Physical evidence of events that occurred in a previous universe, before our Big Bang, before our time, before our laws of physics applied. Penrose is not describing a philosophical speculation about what came before the universe. He is pointing at specific, locatable spots in the sky and saying the last fires of a dead cosmos left their ashes there, and we can see them. Number 2. The Axis of Evil. In 2005, Kate Land and João Magejo of Imperial College London published a paper that gave one of cosmology's most disturbing anomalies a name worthy of it. Analyzing data from NASA's WMAP satellite, they had examined the temperature fluctuations of the cosmic microwave background and found something the standard model of cosmology explicitly and categorically forbids. The universe, they reported, had a preferred direction. They called it the axis of evil. The cosmological principle, the same foundational assumption challenged by the great cosmic web, rests on the idea that the universe has no special axis, no preferred orientation, no direction that is meaningfully different from any other. This is not a minor theoretical convenience. It is a load-bearing assumption in every cosmological model we have built for the past century. The CMB's temperature fluctuations, analyzed through their mathematical components, called the quadrupole and octupole modes, are not randomly distributed as the principle demands. They align with each other, and they align with the plane of Earth's orbit around the Sun, a coincidence so improbable it suggested either a profound discovery or a profound error. In 2013 and again in 2015, ESA's Planck satellite produced the most precise full-sky CMB maps ever made. The axis survived both. The alignment was confirmed with independent instruments, independent teams, and independent methods. The probability of it occurring by chance in a standard cosmological model is approximately 1 in several hundred to 1 in several thousand, depending on the statistical approach used. Scientists have proposed explanations ranging from a previously unknown topological feature of the universe, meaning the cosmos itself has an overall shape or boundary, to residual rotation from a state that predates the Big Bang. None have achieved consensus. The axis also appears to correlate with the direction of the CMB cold spot, and with the phenomenon known as dark flow, in which hundreds of galaxy clusters move in the same direction at speeds that cannot be accounted for by known mass distributions. Multiple independent anomalies may be pointing at the same underlying cause, something built into the structure of the universe at the moment of its birth, or before it. An axis is not something a universe acquires by accident. If the cosmos was born with a preferred direction embedded in its oldest light, something before the Big Bang chose it, and that something left no other trace, we have yet found. Number 1. The Hawking Points. In November 2018, Roger Penrose, together with Daniel Ahn, Krzysztof Meissner, and Paweł Narowski, published a paper that took the CCC ring analysis further than anyone had gone before and made a claim that reframed everything. Scattered across the cosmic microwave background, they reported, were specific, locatable regions of anomalously high photon density, points of subtle excess brightness in the oldest light in the observable universe. They called them Hawking points, and if they are real, they are not part of our universe. They are the last transmission of a universe that died before ours was born. The logic follows from Stephen Hawking's own most celebrated theoretical prediction. In 1974, Hawking demonstrated mathematically that black holes are not permanent, that they slowly radiate energy and, given enough time, evaporate entirely. A stellar mass black hole would take approximately 10 to the power of 67 years to evaporate. A supermassive black hole, the kind that sits at the center of a galaxy, would require something in the region of 10 to the power of 100 years. Our universe is 13.8 billion years old. No black hole in our cosmos has had anything close to the time required. But in a previous aeon, under conformal cyclic cosmology, black holes would have had exactly that time. CCC predicts that as those ancient black holes reach the end of their unimaginable lifespans, their final burst of Hawking radiation would produce a specific, identifiable signature in the CMB of the next universe, a point of concentrated photon energy, a bright whisper pressed into the fabric of creation. Penrose's team identified approximately 20 candidate Hawking points in data from ESA's Planck satellite. Independent researchers challenge the statistical significance of the findings, and the debate continues in the literature. Penrose's team published a detailed defense in 2020, maintaining that the signal exceeds what random noise would produce. The question has not been settled. What hangs on the answer is almost too large to hold. A confirmed Hawking point would not merely be an old object. It would be an artifact from a previous reality, a physical relic of a cosmos that existed, expanded, aged, and died across timescales our mathematics can barely express, before our own universe ignited from its remains. The Hawking points are not ancient by the standards of our universe. They predate the concept of a universe entirely. We did not emerge from nothing. If Penrose and his colleagues are right, we emerged from the wreckage of everything that came before, and the proof is written in the sky above us tonight, in the faintest, oldest light that exists, waiting for us to learn how to read it. If you want to see more videos like this, click the video on screen now and make sure to subscribe.